Hey guys, today we're back looking at 12.2 again, but today we're going to be looking at exponential models. So if you collect data and you notice that it has a curve to it, one of the options might be that it's exponential growth or exponential decay. So again, in its basic form, we might have something like y equals a times b to the x power. Unlike with our power models from yesterday, when we had those, our exponent was a constant. We called it p, and it was something like y equals x to the p power. Today we're looking at our base is the number and our exponent is the variable, and that's called an exponential. So if that base is multiplying by a number that's greater than 1, that's when we had exponential growth. And if b is a number or decimal or fraction between 0 and 1, then it represented exponential decay. So a lot of times, obviously, the statisticians that are collecting data would have some understanding already about what it is that they're collecting information on. And in context of different fields, bank accounts, I spell accounts, would have some sort of interest where you're making money on money. So bank accounts have this exponential growth type situation. We also see it with population growth. So if you're looking at a population, whether it's bacteria or the spread of a virus, bunnies multiplying, because you're doubling or tripling the same amount all the time. If you keep multiplying by 2, that growth is going to be exponential. You would have this type of model that you would see. For decay, we see decay happen in different isotopes. So if you're looking at radioactive material, or if you're trying to age a bone or something, like you're looking at how that chemical is breaking down over time, that's when we would see decay models. So again, they would already kind of know or understand what type of situation that they're looking at, so that when they see their data, they're going to know, oh, this is an exponential model. So we look at this curve and we see the pattern in the bacteria over the amount of time. And maybe you remember even how to calculate it, but to figure out what it is we're multiplying by every single time, because our formula may not be exact, like you're collecting information, but it kind of looks like, from 6 to 18, I know they multiplied by 3. Is that the pattern? And if you work backwards, if you remember Algebra 2, you can find the y-intercept, like the y-intercept is 2. If you go backwards, so this would be something like y equals 2 times 3 to the x. Now that's my exponential model for this data, but how do we get there? So how do we make sure, or how do we even figure out what we could do to predict stuff? So one of the options that we have is to take the log of just the y's. So because those numbers are getting bigger and bigger and bigger and bigger, if we take the log of our y values, and down here it says the log of the bacterias, now we see a graph of our x's here, which were time. That's the same that we had over there. Instead of having us graph bacteria and see this exponential growth model, if we change it and now we're looking at the log of those bacterias, we get smaller numbers. So if we then go through and graph time versus the log of the bacteria, we end up with, new data points, and it shows those, let's go orange here. Like each x is still x, each y is now the log of y, and we see now it makes a more linear looking graph, okay? So our job is to then go through and create a line of best fit that goes through this data. But when we do that and create our least squares regression line for our y hats, what are we predicting now? We're predicting the log of the bacteria, not the bacteria. And then we have to go through and solve that. Okay. So first step would be to put, time in list 1. And then you can put, typically we would have our bacteria already in list 2. And then if we do list 3 is the log of list 2, we could generate all of these numbers there. And then when we make our least squares regression line, we're looking at list 1 versus list 3. And it'll give you an A value I got of 0.301 and a B value of 0.477. And then we're going to be asked to write our least squares regression line. Okay. So we've already defined X as time. We've defined Y as the amount of bacteria. So our entire graph now, if we're looking at our list 1 versus list 3, should be, we're predicting now the log of the bacteria would be A plus B, and our X this time is time. Okay. So just double check that you can plug in that information and that you get the same prediction line I did. Okay. And again, they might define those variables as X, and then over here you have actual log Ys, and then our prediction line. We're going to use that prediction line then to find the number of bacteria after 3.5 minutes. So here we're going to plug in X is equal to 3.5 minutes in for our time. So most of this is just like, don't stop once you find what you've plugged in. So if I plug in 3.5 and multiply first because of PEMDAS, and then add, you should get that log of the bacteria is 1.9705. Okay, so this is what I mean by don't stop. Plugging in 3.5 into our equation, we plugged in 3.5. It's predicting we're going to get out 1.97. Right? But this is predicting the log of that bacteria. What does that mean for the actual bacteria? So how do we go back and undo a log? Well, common logs like this one, where the base isn't written, the base is 10. So whenever there's not a base written, that's automatically a base 10 log. So to undo this, I would need to exponentiate both sides with a base of 10. 10 to the power of log of that bacteria would just now have me predicting the actual number of bacteria. I guess plural, it should be bacterium. So that's 10 to the power of 1.9705. Okay. So 10 to the power of that now exponent should be 93.4 bacteria. Okay. So does that make sense? when we plugged in 3.5, in between 3 and 4 minutes, we have between 54 and 162 bacteria. Makes sense. Okay. Why does that work? So if you go back to look at rules of logarithms, which basically are your rules for exponents, there were some log properties that you were supposed to learn back in Algebra 2. So some log properties that you may have forgotten. Like I forgot how to spell properties. Should be that when you're multiplying, that's the same as adding two separate logs. Okay. And if you're raising a log with a power, that's the same as multiplication. So one thing that we notice is if we're trying to solve this, in that original function I kind of showed you, y was equal to 2 times 3 to the x power. You started off with a y-intercept of 2, and you were multiplying by 3 each time. And weirdly enough, when we take the log of both sides, because that's how we fix this, or sorry, if we just take the log of the y values and not both, that means you're doing the log of that 2 times 3 to the x power. But here we said when they're multiplying two logs inside, if you expand that, that's really, it would be the log of 2 plus the log of 3 to the x power. And with that exponent that they had on there, what that does when you expand it is it's going to drop down in front of that log and show us x times log base 3. So when we went through and calculated and we got our a and b value, that's why these look familiar. The log of 2 is about 0.301. Well, 0.301 in our linear regression was the a value. Okay. And if we were to go back and look at what our b value was, our b value was about 0.4771, which from our regression equation was b. And so that came from, like, that's what the log of 3 is. So there's this connection between our linear regression model and what the exponential function looks like. Okay, so we're not asking you to write exponential functions. We're asking you to take an exponential function that you may not even know what it is, but recognize that it's exponential growth or decay. Take the log or natural log of just the y values to make it linear. Okay. And then do a least squares regression line on that and be able to plug into it and solve backwards. This concept of undoing a log with its base is huge, but we don't deal with any other types of logs besides the common log, which is base 10, and the natural log, which is base e. So we're going to look at that in just a minute as well. And in our notes for exponential functions, I'm just dealing with the first type, just taking the log or natural log of the y values, because typically that's the number that we see that's much bigger. If you see very large numbers in your x column, then I would want to take the log or the natural log of just the x's. But here we see with this next problem for light intensity, we also see very large values for our light intensity. So I'm going to take this time the natural log of the light intensity. So here it's straight out of our textbook. This is number 38. They have the depth versus light intensity. Okay. And I think the scenario is they're diving in the ocean. and they're trying to measure, like, as they dive deeper, how much light is penetrating through to that ocean floor. So if you make a scatter plot by hand or by using technology, like right now, you have your X and your Y variables. And I'm going to do a really crappy job. Hopefully you're better than I am. But 6, 7, 8, 9, 10, 11. These numbers go all the way up to 168. I don't know what our units are quite. Looks like depth is measured in meters. And then light intensity, I think, would be in like lumens. So as you're diving deeper, oops, 120. Okay, we see, a curve. And eventually you might get close to zero, or you might, I don't know if you'd actually reach zero in this case, but we should kind of see that horizontal asymptote taking place. They're never going to get negative as you're going down. You can't have negative light intensity. So that's another key kind of factor with our exponential functions, is they should have some sort of horizontal asymptote that they're reaching. As x goes into infinity, y is going to 0. All right. So there was, what do we see? We notice a nonlinear pattern. So I don't know necessarily if you remember, but hopefully we do. When we were looking at scatter plots, you were supposed to use cussing to help you remember. Oh no, I'm wrong. Cussing was for normal distributions. Here we want to use defs. So direction. So there seems to be a negative association. Unusual features, nobody's unusual. Form, if you recognize that it's exponential, you can say that it's exponential, or you can just say that it's nonlinear. And then you should also talk about the strength. There does seem to be a very strong nonlinear negative association between these two things. Okay, so you would use all of that to kind of make a good sentence. All right, so there appears to be a strong negative nonlinear association between depth and light intensity. All right. Here we have regression analysis output into a mini tab. So remember how these things work. You have a bunch of stuff kind of given to you. The ones we care about, like they give us depth. They also give us our A and our B value. The other thing that we're kind of skipping this year is the T and the P values. Like, you're not looking at those. You do want to know what S stands for, and you want to know what R squared stands for. So using all of that together, that's a very good R squared value. We ignore the adjusted and all that kind of good stuff. But for us, like, there's X, there's A and B. This is the standard deviation of the residuals. Okay. And that R squared is called the coefficient of determination. It's the percent of variation in our light intensity. that is explained by our depth. Okay. So it says give the least squares regression line based on this. Well, be careful, because this is why we need to know this chapter. They have depth versus the natural log of the intensity. So they recognize that in part A, it was strongly nonlinear. So they transformed the data so that they were able to run linear regression on it. Because you can't run linear regression on something that's not a line, or at least you're not supposed to. So when we go to write this, we have a prediction of the natural log of that intensity. Okay. And it's equal to A plus, minus, slope is negative 0.33. Okay. And we're plugging in depth. So if you want to define X and Y, you can, but I'm just going to use the word. So the natural log of intensity is a thing that we're predicting. And then just like yesterday where we plugged in, we want to do the same thing. So use that model to predict light intensity at a depth of 12 meters. So this is where we have to, again, pay close attention and know how to solve natural log equations. If we have a prediction for a natural log and they're asking us to go back and find the answer for actual light intensity, we better be careful about what numbers we're choosing. So this is where, think a minute, like 12 isn't in our domain for the collected data, so be a little bit careful. But if you're plugging in 12 for your depth up here, I know it's got to be less than 22.78. All right, so we're going to plug that in. X is 12, or depth is 12. If we predict the natural log of the intensity, 6.789 minus 0.33, I rounded that, plugging in 12. Multiply first. Then subtract. I'm predicting the light intensity's natural log should be 2.829. Okay. So now we still have one more step. We have to go through and get rid of the natural log. So just like in the last problem, I got rid of the log with its base. With the word log, that common log, the base was 10. For natural logs, the base is E. So to kill off the natural log, I'm going to base E both sides of my equation. And then I'm left with my prediction for the light intensity should be E to the power of 2.829, which is about 16.3. So second ln 2.829. Yeah, 16.93. And then I have lumens. Okay. So if you didn't round, you'll get something slightly different, but that's okay. Make sure that it looks appropriate for your graph. If I plug in 12, does it make sense on the original scatter plot? I think it does. So about 16 point whatever lumens. All right. So going back, and we kind of want to compare the two different days. What's the difference? The difference should be power models are going to be transformed differently than our exponentials. For our power models, they look something like y equals, x to the, I'll still use that x to the p. We had an a in front of it yesterday. For our exponential models, they're a little bit different. So where is the variable versus where is the constant? Here you had a power. And today, for the exponentials, like x is the exponent. Okay. So if you know the difference, how do you fix them? So our transform options here, keep x alone, raise y to the reciprocal power, or take its root. That would be the same thing. Our second option would be to raise x to the same power as y. And our third option would be to take the natural log of x and the natural log of y, or you could take the common log of just both x and y. Okay. Today, our transformation options. Our first one, and the only one that we really saw, was taking the natural log or log of just y. Our second option would doing just the natural log or just the log to the x's. And again, it really just depends on where you see the drastic change in the numbers. If I saw the drastic change in the numbers in the x column, I would do the natural log or log of the x's. Okay. So the one that we think is most typical, if we have to go back and look at them, we see a lot of transforming just the y's. And on the first day, what we did yesterday for transforming options for power functions, we saw a lot of doing it to both. And the reason why we saw that is because typically we may not know this power. Okay. So if you don't know what the power is, it's hard to undo it. All right. Let me know if you have questions.